When a hot object and a cold object are brought together, one cools down and the other warms up, at least until they reach thermal equilibrium, where the temperatures are equalized. But there is something important that we are missing here. How does energy fit into this picture? What actually flows between the two objects to change their temperatures? In this video, we are going to investigate this. First, we'll see how energy is involved in this exact scenario, that is, via heating. From here, we'll deduce that there must be some sort of internal energy within thermodynamic systems, which is affected by heating. After this, we'll identify any other ways that energy can flow in and out of a system, such that the temperature changes. And finally, we'll bring these ideas together with one of the most important results in physics, the First Law of Thermodynamics. This will provide us with an exact equation for tracking how energy moves in and out of thermodynamic systems. We'll also make clear how and when it applies. So let's start again from our simple experiment involving two iron blocks. Using a thermometer, we find that the first has a higher temperature and the second has a lower temperature. When we bring them into contact, after a short while, they reach thermal equilibrium, where their temperatures equalize. So we know that the temperature of each object changes during this process. But if the objects are changing in some way, something must be transferring between them. And it can't be temperature, because temperature is a property of the objects themselves. You can think of it as a signal that tells us whether this something is going to be transferred from one object to another in the first place. Of course, this something is energy. Which direction does the energy move in? Well, think about how hot objects behave versus colder ones. As you increase the temperature of something, it goes from solid to liquid, then to gas. A liquid is far more mobile than a solid, and a gas is far more mobile than a liquid. Hopefully, it is intuitive to you that when the same object is hotter, it is more energetic than when it is colder. So in our temperature equalization process, energy is flowing from the hotter object to the colder one, until their temperatures equalize. This specific type of energy transfer, which we observe everywhere in nature, is called heat. Heat is the energy transferred between systems due to temperature differences. This is all purely observational, by the way. All we've done is identified that objects with different temperatures tend to evolve toward the same temperature over time, and they do this by transferring energy. We haven't yet figured out why this occurs at all. We'll get to this in later videos. But even without this explanation, we can still say something important here. When we heat something, it is gaining energy. Since energy cannot be created or destroyed, it must be stored inside the object somehow. We call this store of energy the internal energy, U. We do not yet know exactly what contributes to the internal energy, and we do not need to. What matters now is that internal energy is a property of the system, and that heating can change it. We also know that the internal energy is linked to temperature in some way. The exact relationship is a bit more advanced, so we will not worry about it yet. So this begs the question, is heating the only way to change a system's internal energy, and therefore its temperature? This leads us to a very important historical experiment, involving a gas sealed in a cylinder, with a movable piston on top. The gas is trapped inside, but the piston can slide up and down. Initially, the gas is in thermal equilibrium with its surroundings, meaning there is no temperature difference, so no heat flows in or out of the system. We now push the piston down, compressing the gas. When we do this, interestingly, we find the temperature of the gas increases. This is an absolutely crucial observation. All we have physically done is modified the volume that our system, the gas, exists in, and in doing so, we've seen that the temperature can change. This change did not happen because of heat, because the gas was already in thermal equilibrium with its surroundings. Instead, we forced the piston downwards, and in doing so, we transferred energy to the gas through work. We applied a force through a displacement, in this case the piston, and this energy changed the internal energy of the gas. And this isn't the only example of work changing temperatures in nature. For example, in the 18th century, Benjamin Thompson observed that drilling metal to make cannons generated a lot of heat, so much that water could be boiled. Also, this idea of work isn't limited to pushing pistons. It also includes things like electrical work, which does occur in some scenarios. So overall, we've shown that we have two ways to change the internal energy of a system, heat and work. We can write that the change in internal energy, delta U, is equal to the heat applied to the system plus the work done on the system. All we are doing here is stating that energy is conserved in nature. This simple equation is also known as the first law of thermodynamics. Often, you'll see the first law written as delta U equals Q minus W, where W is the work done by the system on its surroundings. When we have Q plus W, we are doing work on the system instead. If you're still confused, to get the signs right, just think about whether the system is gaining or losing energy in that process. Now this equation might seem overly simple. Surely there are more ways of changing this internal energy. Well, there are, but only if we allow mass to enter or leave the system. If we let some of the gas out, then we'd lose some of the mass and therefore energy. So we need to say one more thing about the first law. We are dealing with the internal energy of a closed system. For a closed system, where no mass crosses the boundaries, in this case the container, the only way we can change the internal energy is through heat and work. And that's all there is to it. By the way, if you're enjoying this video, check out the Decipher Physics app and websites, which have interactive lessons and practice questions for this video and others. It's completely free to use. So let's summarize what we've done in this video. First, we established that when two systems with different temperatures are brought near each other, energy in the form of heat flows from the hotter system to the colder one until the temperatures equalize. This allows us to conclude that each system must have some sort of internal energy store, which changes as heat transfers. We also deduced that temperature must somehow depend on this. After this, we found that there are other ways we can change the temperature of things in nature via work. This work also changes a system's internal energy. This allowed us to write the first law of thermodynamics, that the only way to change the internal energy and therefore temperature of a closed system is via heating or doing work. So delta U equals Q plus W. We emphasized that this applies to systems that are closed, such that no mass can escape the boundaries. Overall, we have now stated the conservation of energy in the context of thermodynamics. But there are still unanswered questions here. The first law tells us how energy changes, but it does not tell us anything about why processes happen in a particular direction. It does not explain why heat energy flows from hot to cold, and never the other way around. In the next video, we are going to explore all of this. In doing so, we will uncover the second law of thermodynamics. Thanks for watching.